Hi guys, it's Daniel here, and today we're going to do a CleverMath problem. This is a combo 150 from last week. It's called Joey's Dice. So let's start by reading the problem. Joey rolls two standard six-sided dice repeatedly, noting that the sum of the numbers on both dice. She stops when she obtains a sum of 12 or two consecutive sums of 7. And we want to find the probability that Joey obtains a sum of 12 before two consecutive sums of 7. So to begin with this problem, let's first find the probability that she gets a 12. Well, this is easy. You just roll two sixes, which each have a probability of 1/6. So the probability of rolling a 12 is 6 times 1/6 times 1/6, which is 1 over 36. Now, what about the probability of rolling a 7? Well, we can roll a 7 by either rolling a 1 and then a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. There are 6 ways to do this. And each way has a probability 1 over 36 of happening, so our probability here is just 1 over 36 times 6, which is equal to 1/12. 1/6. And now finally the probability of rolling any other number. The probability of rolling any other number. Well, this is just 1 minus 1 over 36 minus 1/6, which is just 29 over 36. So now we have our probabilities distributions of either rolling a 12, a 7, or something else. And now we can start solving the hard part of the problem. Now, I'll show you two ways to solve the problem. The first way is more standard, a little bit more tedious and difficult way to solve the problem. And the second way is the much quicker but far harder to see way. So let's start by solving it the first way. So to start off, we want to find the probability of something happening before something else, which may go on over, like the rolls may go on just like 2 rolls, or it may go on for like 100 rolls. So we don't know. But if we just calculate it directly, then there'll be way too much casework. So instead, let's define a recursive formula. So first, let's let the probability of what we want happening as p, and we'll try to find a recursive formula for p. So we know that p is equal to the probability of rolling a 12, which is 1 over 36, plus the probability of rolling a 7 and then a 12, which is 1/6 times 1 over 36, plus, well, if we roll two 7s, then we lose, so that can't be in p. So what else have we left out here? Well, we've left out rolling any other number, and then, which that brings us back to our original problem. So, for example, if I roll a 5, then the problem has just been reset, and I've just returned back to what I originally wanted to find. So, in this case, we multiply by p at the end. And finally, the last case that we haven't considered yet is rolling a 7 and then rolling any other number. And this has a probability of 1/6 times 29 over 36. And again, we see that after we roll any other number, we return back to the original problem. So we multiply this by p. And now we have a recursive formula for p, and we can solve it. And I'll skip the calculation, don't want to bore you here, but we end up with p equals 7 over 13, which is our answer. Now this is the long way to do it. It's more reliable, and it applies for a lot of problems, but it's a little long and you might make some mistakes on it. But this second solution I'll show you is a much faster, a much more clever and slick solution. So in this solution, for convenience, I'll just let rolling a 12 be A, rolling a 7 be B, and rolling any other number be C. So let's think about it like this. If we roll any other number, then we've just returned back to our original problem. So what if we just considered what happens in the end game? In that case, what happens when Joey finally gets a result? If we just consider this, then maybe we can find the probability of getting what we want and finding the correct answer. So in this case, the end game happens when we roll an A. That's one case. If we roll an A, then we win, and that's an end game. Another case is rolling a B and then another B. In this case, we lose. And one more case is rolling a B and then an A. We can check that there are no more endgame cases because we can't roll an A and then the B since we already rolled an A. And we also can't have C because that doesn't do anything to the endgame. So at the end, when we finally get a result of either winning or losing, these are the only three cases. The probability of getting an A is, of course, 1 over 36. The probability of getting two B's is, of course, 1 over 36. And the probability of getting a B and then an A is 1 over 216. Now, let's see which one of these cases do we win. Well, clearly, we win this case, and we win this case. The only case we don't win is the BB case. So now we're given this problem. Given that, in the end, we have these three cases that happen, what is the probability that this case or this case happens? So we have this conditional probability question that we need to answer. Well, first let's put everything in under common denominator. This is 6 over 216. This is 6 over 216. And this is 1 over 216. Now, because we're doing conditional probability, the denominator becomes 6 plus 6 plus 1, which is 13. In the numerator, the cases where we get what we want is, of course, 6 plus 1, which is 7. And this is our correct answer. As you can see, this is much faster than solving this ugly system of one equation, one variable. And if you're still a little confused here, I'll explain it one more time. So in this second solution, we don't care about anything that happens in between that prolongs the game. All we care about is the end game, what happens at the end, either winning or losing. So at the end game, there are three cases. Either we automatically roll an A and we win, or we roll two B's and we lose. Finally, we can roll a B and then an A and we win. Note that if we roll a C, then it doesn't matter, since rolling a C doesn't affect winning or losing in any way. It just prolongs the game. So rolling a C does not affect the end game in any way. And you can check that A, BB, and BA are the only three scenarios of the end game that are possible. Anything else is contained within these cases. And thus, we can assume that one of these three cases happens and find the probability that either A or BA happens, which is what we want, which is when we win. And the probability of A or BA happening, given that A, BB, or BA happening, is 7 over 13. So we're done.
Hey guys, Long here, back with another math video. Today we're just going to be taking a break with a relatively simple geometry problem because I know school is starting for a lot of you. So let's just chill a bit and